So I'm particularly pleased to be able to introduce Nika Haghtalab. She works on exactly the right things to be working on. So Nika's an assistant professor at Cornell University in computer science. She has done postdoctoral work at Microsoft Research. And she originally comes from Carnegie Mellon, where she did sort of econ, machine learning, and so on and so forth. So she's kind of been all over these topics for quite some time. Leading person in what's called the EC community, economics computation. So I think a lot of you know that I've for many years pushed that computational thinking isn't anything. There should be this thing called inferential thinking. That's kind of a Berkeley signature. And you may also know that in the last few years I've started to decide there's a third part of that tripod, which you might call strategic thinking or economic thinking or whatever, or one of those words up there. There aren't that many people who kind of presciently been working on that kind of mix of ideas, that you have to think about decisions in the context of strategic situations with other people making decisions, and how that relates to people, and how that brings computation and data together with people. So Nika's a leader in that, and just before I turn it over to her, one more thing was, I knew she was a leader when I first saw her thesis title, because her thesis title, if I remember right, was something like Machine Learning for the People and by the People.
Foundations of.
Foundations of, even better, yeah. So you know, that's a real thought leader kind of thing to do, is put it out there, you know, the title of your thesis. So anyway, I'm glad to have Nika. Thanks for coming.
Thank you very much. Thank you very much for the introduction, and thank you all for being here. I'm really excited to share some of the projects that I've been thinking about more recently. Of course, it's not a surprise that machine learning has had many successes in the world, and in particular, it has revolutionized, you know, the way we think about our day-to-day lives, science and technology. And one of the, you know, thanks in part at least to machine learning, we've seen huge leaps in many applications like natural language processing, image processing, and applications in bioinformatics, and many, many more. One of the main questions in machine learning is how would we think about designing and analyzing algorithms that can learn some general facts about a process that's creating data by looking at some limited amount of this data. And when it comes to this question, one of the areas that modern machine learning has really excelled in is to think about prediction as a model of learning. And here, the main question that people think about is that if I have a feature representation X, that there is some Y that's correlated, I'm trying to learn this label, how can I do that? And in particular, if this is coming from some distribution of instances that I see in practice, how can I learn this Y from the representation that I'm seeing? And this is prediction. And you can think about this as an example of, you know, your X's being images of cats and dogs, and the question that you're asking is whether this is a picture of a cat or a dog. But when we think about applying these techniques to decision making that, you know, the human subjects are actually concerned, many things change in this picture. And one of the issues is that now label Y actually has a meaning, has an implication for that person or entity that's going to be classified. This means that it might mean that a person will get to go to college or not, get to be selected for an award or for being waitlisted on, you know, on a patient, you know, medical care. And because of this, it means that people have incentives to actually change their representation. And maybe not quite as much as, you know, poisoning the other candidates, but still quite a lot of incentives go into changing either your representation or the environment that you're in. So now there is an interaction between X and Y, which was not in a single direction before, There are also changes in the environment that sometimes are as the result of the earlier decisions that we've made. And at other times, it might just be because there are some other natural phenomenon that's happening to, you know, people, and their behavior is changing as a result of that. So because of that, it's unrealistic to assume that we have these distributions of instances, and we need to work with whatever this environment is presenting to us. And lastly, these decisions have a lot of long-term, you know, impact, downstream impact. For example, making some mistakes or making decisions that are not fair or biased at this point can really get exacerbated over time. And because of this, actually in high-stake decision-making, humans are very much involved as decision makers as well. So what we are going to see is how we can think about this decision making when we have either human decision makers or human subjects. And for this talk, I'm going to focus on some of the key challenges that we just discussed, which is how can we think about decision making for human subjects when we need to think about environments that are potentially evolving over time, and there are uncertainties in these environments, sometimes as a result of policies that we've implemented. We also want to think about human decision makers, where we have these human domain experts with knowledge, and we want to think about how can we augment their and increase their capabilities while reducing some of the mistakes and other human inefficiencies that there's there using machine learning. So for this talk, I'm going to talk about 3 different interrelated projects. The first one is about robustness to dynamics that exist. The second part is how can we actually, rather than tolerating and be robust to dynamics, create good dynamics. And the third part is about how can we improve human decision making in these processes. There are also a number of other important perspectives here that I'm not taking, but I think they're very important, and I'd love to chat with you if you're interested in them. And these are more about just robustness of machine learning, more generally speaking, dynamics that are involved in data collection, fairness, and equitability over a long period of time. The social learning aspect of when people are actually learning from each other and making decisions based on these relationships. And also, in general, how can we learn a lot more about strategic agents when we're just seeing some of their actions and don't know exactly what their thought process was. So if you have any questions during the talk, please feel free to ask. And I'm going to start by, in the first part, talking about robustness to dynamics. And this is a joint work with Miro Dudek, Haipeng Liu, Rob Shapiri, Basilis Organis, and Jennifer Worthman. And what I'm going to talk about broadly applies to decision making and thinking about policies that we set that will impact people. But for the sake of simplicity, I find auctions to be one of the examples that people get the best. So we are going to talk about auctions. Auctions are these mechanisms that will take preferences of people about certain items and then decide who should get what item and how much they should be paying. There are many different types of auctions, and a common misconception is that there's just one type. You give the item to the highest bidder and charge them how much ever they said they were willing to pay. But there are many reasons for you not to run this auction. So for example, you may want to not give the item to the highest bidder because you want to encourage people to bid higher and higher if they can. But at times, you might want to actually put a reserve on your auction so that if you do end up selling an item, you've made sure that there was some minimum revenue that you made. And because of this, actually, the field of auction theory is huge. There are many different aspects of auctions that are important, and people really pay attention to them. And of course, revenue is one of those. So there has been a very long line of work for decades thinking about how can we create revenue maximizing auctions. And the main question of interest there is that if I have been given a class of auctions, I will represent it as X, and people's valuations coming from a distribution D, what is the auction that has this highest expected revenue? And this question has been looked at from the perspective of economics of what are the characteristics of these auctions, but also in terms of how many even samples do I need? How much information do I need from distributions of valuations of people? But what we are going to think about today is that this assumption that there is a distribution where valuations are coming from is actually not a very realistic one. In auctions, the demand of people changes over time based on items, based on many things that happen in practice. Holidays coming, the stock market reacting to many other phenomena. And because of that, actually the valuations of people keep changing, sometimes in ways that you cannot predict. And the challenge when you're designing auction, when you have these changing valuations, is that when valuations change, the historical performance of an auction is no longer a good indication of how well it's going to do in future. So what you want to do is to still learn these optimal auctions, still knowing that these valuations can change over time. So we want to be a lot more careful with our learning process. We are going to think about the scenario or use the model of online learning for this. In this model, you have T time steps. At every time step, one auctioneer decides on the parameters of the auction that's going to run. So these are, for example, reserve prices that you might set in a day. And then the world will present some potentially adversarially selected valuations of people, shown by bid profile or the valuation profile YT. Then the auctioneer gets to see what this valuation was and will receive the revenue for running the auction on this set of valuations. So for people who are familiar with online learning, this is called the full information setting, although I also work on the banded information version of this as well. So the objective that we have is to minimize regret. Regret is the difference between the revenue of our auction throughout T time steps versus the revenue that the best auction could have achieved if I knew the sequence of valuations ahead of time. And this is formally shown here. The question of designing no-regret algorithms goes actually back to a couple decades ago and is much more general than designing auctions. So in the more general setting, you're thinking about a learner that's living and making decisions in a potentially adversarial world. And you want to make sure that the learner can get a regret that is going to be sublinear in the number of time steps T. What that means is that on average, or the more the learner plays this game, the better it gets at it. On average, the regret is going to 0. And there are really interesting and general purpose algorithms that have been there since the 90s that tell you that you can have these general purpose no regret algorithms. The regret is square root of T and logarithmic in the number of auctions or the number of actions that were presented to the learner. And these are really nice because, as the size of the choices that the learner can make increases, even exponentially, the regret is increasing very slowly. So you can still effectively learn. But one of the challenges here is that these general purpose algorithms have a runtime that is linear in the number of actions that are available to them. And in auctions, this is the number of auctions that we have to be working with. And as I just told you, the challenge here is that the number of auctions, like in many other policy setting questions, is really large. This is because there are a lot of parameters that we want to think about. Maybe we have multiple items that we need to decide how to price them individually or bundle them together. Maybe it's because I want to have some provisions to provide discounts to students and seniors and maybe not to others. So the more parameters I start to care about, the larger this set of auctions becomes. And this linear runtime now becomes a bottleneck that I cannot run my auction within reasonable time anymore. Nevertheless, there are these effective tools for finding optimal auctions when the valuations were coming from some historical distributions. These are either actual polynomial time algorithms, but also in many cases just highly optimized algorithms that run really well and fast and well in practice, but might not have runtime guarantees. What you're going to show is that you can directly tap into these existing tools and make them be robust. That is, without actually changing these tools, you can make them compete with the best auction even when your preferences are changing. And this is called Oracle Efficient Online Learning. To be a little bit more concrete, in Oracle Efficient Online Learning, you're making an assumption that you have this oracle with a certain power. The power of this oracle is that it can compute and solve historical problems for you. So if you're given a set of actions or bid profile y1 to yt, these are things that the adversary would have chosen, you can find the action that would have maximized your utility over these historical bids. So given this power of Oracle, people have been thinking about the design of online algorithms for quite a while. It was shown in 2005 that you can have these Oracle efficient algorithms if your function that you're maximizing is actually like linear, but maybe in a lower dimensional space. More recently, it was shown that if the number of actions the adversary can take, which is, remember, our bid profiles, is small, you can again have Oracle efficient online algorithms that run fast in practice. But unfortunately, we also know that this progress will stop at some point because there are scenarios that you cannot have an Oracle efficient algorithm, even if you have an Oracle. So what we are going to see is that there is this, yes?
So I'm trying to visualize this from the viewpoint of Christie's, the auction house. So they have, as their input, they know more about all the previous sales at all the other auction houses. So they have a good record of what's going on. Now, what are they supposed to do here? They already know everything. You're going to recommend to them how they should take all that known information and how they should conduct the auction. Is that your goal?
That's the goal, but Christie is a hard example to think about because their value of auctions is really high. So I would say think about auctions that are cheaper per run of the auction. So like ad auctions, like per run could be like a little bit, for some examples, could be cheaper. But yes, think about these auctions that you're running every day for similar types of item, but for different people or people whose valuations may be changing. So Christie is not the best example because both the set of people is changing, the set of items is changing. So it's a little bit of a different example.
So it's like treasury bills, those are sold every day.
Yeah, so you can think about this exactly. So you get like the historical information of how well, the previous auction, the bids, what were the bids in the previous games, previous rounds, how well would have an auction done, and if you didn't care about the dynamics part, the fact that potentially, there are these changes, what you would do is actually you would run your Oracle. You would just say, take the historical data and do an optimization on it, and that would be what the solution for you would have been. But we don't want to do that, again, because the changes in valuations can really mess this up. But we want to now still use the historical information, which we should be using, but use it in a more responsible way. Any other questions? And is this clear what the power of the Oracle is? OK, so I said that there is a structure space that if your problem happens to have this structure, you can show that there are online Oracle efficient algorithms for it. But also, more importantly, many auctions in general, many combinatorial problems and many policy setting problems happen to show this kind of a structure. So you can solve and optimize them over many time steps using the same algorithm. Let me tell you a little bit about what this structure is and why we see it a lot in practice. We say that a problem has a D structure if there exists a set of D adversary strategies, here bed profiles again, that sufficiently distinguish between actions, any two actions of the learner. So if I wanted to think about this, I can think of a game table where the rows refer to the actions of the learner, the columns refer to the actions of the adversary. Having a D structure means that there are D columns that if I remove the rest of the game table, any two rows are still sufficiently different from each other. So this is a D structure. And what we have shown is that if you have a D structure, then you have this general purpose Oracle efficient algorithms with a regret that is linear in D and square root of T. The other thing we've shown is that most auctions that you can think about have a D structure for a value of D that is a small polynomial in the number of bidders that are present in your auction. And I want to actually start with the second point and show to you why many auctions at a very high level have this property. The way to think about this is that, so what we need to see is that there are polynomial many number of bid profiles that distinguish between any two auctions and parameters of auctions that you may be choosing in between. And even though there could be a lot of parameters when you're deciding what the outcome should be, when you look at the outcome, you can sort of work your way backwards and say which parameters were actually important for that outcome. So for example, in most auctions, only the winner, maybe the second in line to winning, and how much they bid or how much their reserves were, are important features that come into the computation of your outcome. And because of that, this actually allows us to think about very simple bid profiles that separate and distinguish between all of auctions. Because if two auctions are different, it meant that they were different on some bid profile. And let's say that I take all those parameters that were important to my auction, and I work my way backwards and say, imagine the other parameters were all 0. Nobody else other than the people that mattered actually wanted this item. the effect of the outcome of the auction doesn't change at all. So even though the auction itself is not sparse, the outcome could be described using a sparse set of bids. And the nice thing about the sparse set of sparse bids is that it's much less complex, and the number of sparse bid profiles that you can come up with is much smaller than the total number of bid profiles. And this is why most auction classes have a D structure. More generally speaking, this is also related to interpretability, where in general we think about thinking about interpretable policies. And that's essential part of decision making, because what we want to do is to be able to account for the types of decisions we've made and why we made a certain decision when we saw a certain input. So here, the D structure, what's giving us is some measure of interpretability, in the sense that the difference between any two different policies that I could have used on the same point can be explained using a few features of that point. Like maybe I can take policy A and B and say that they were different on a candidate X because policy A really cared about, let's say, the SAT score of this person, and policy B really cared about their GPA. And the GPA and SAT score of this person were very different. So this is one way to think about why, in general, interpretability of policy classes can lead to them having a D structure for a small value of D. And actually, a cool thing here is that interpretability, people like it for decision making because it allows us to be accountable. But here, the cool thing is that it also allows us to compute and optimize our policies in a really fast way. I want to tell you very little about what our algorithm is actually doing and how it's using this D structure without going into too much details. So the way that we are going to use the D structure is to take the columns, these were adversaries' actions that refer to these columns, and think of them as being sort of injected to our history. So at every step, I use the oracle on whatever historical data I've had, plus some fake history that I'm creating. And this fake history that I'm creating is going to have some alpha I copies of column DI, or the action of the adversary that referred to column DI. So you can think about this as I took the Christie's example or the auction example. I had some real history, and then I hallucinated some history, and I added to my actual history. And now I'm doing this optimization over my hallucinated history. So the nice thing about writing the algorithm in this way is that clearly it's oracle efficient because I'm using the oracle on some fake history. So clearly it's oracle efficient. The main question is this also no regret? And to see that it is, I actually like to write this optimization in a slightly different optimization where there is an actual perturbation or regularization term. And the way to think about this is that I'm choosing the auction whose historical utility plus some random perturbation is optimized. And this random perturbation happens to be a very structured random perturbation. It's the dot product between the vector of random variables alpha I and the row that was representing that specific auction. So this is just another way of writing my previous optimization problem. And the nice thing about writing it in this way is that it actually looks a lot like a family of algorithms, no regret algorithms, called follow the perturb leader. And there we know that if you can perturb all the actions that is available to the learner independently, you can get no regret algorithms. For us, this is a good intuition, but it doesn't actually follow completely through. And the reason is that these perturbations that we are using, these row of x dot alpha, they are actually highly correlated with each other. They're all the dot product of the same vector of random variables with these different rows. So they're not independent, and that's why we can't really use this. But it still gives us some very high-level ideas for how to prove this. And the high-level idea is that the nice thing about independent perturbations is that it creates stability in the problem instance. And stability means that I won't change my action from one day to the next day with high probability. And that's actually sufficient for no regret learning, this notion of stability. So I want to recover stability, and I just say that, well, I don't have independence. X and X prime are actually dependent on, very correlated, but there's still some randomness between them, and that's because the rows are different, so they're kind of being multiplied in a slightly different way. So at some, at a very high level, I have stability for any two rows that I look at, because there is some randomness in between them. But I shouldn't really think about like taking a union bound over all these rows. At the end of the day, I have many rows. If I take union bound, I've completely lost the point of stability. So instead of taking a union bound, I actually use the D structure of the algorithm, this instance space, to cluster all of these bad events to different groups based on which column is causing lack of stability. And then I use that to show that collectively, each cluster of bad events is going to happen only with small probability. This is a very high-level idea. I'm not going to go into this, but if this is just to showcase a very few technical ideas that I find interesting about this problem. If you're interested to learn more about this, please come and talk with me afterwards. And if you weren't interested in this, so let me just say that do not worry. We're not going to go into more details of the technical part. Instead, let's just kind of remember what was the point of what we did in this part of the talk. And that was, we wanted to compute these optimal auctions on changes preferences. And the cool thing was that it came for free. I didn't need to create new optimization tools. I just needed to use the old ones in a more responsible way and in a slightly different way. So that's for the first part of the talk. If there are any questions, please feel free to ask.
So I'm just sort of wondering, if I were an auctioneer and I know the preferences are changing, then I would want to be changing my auction strategy online as well. But when you do online learning, at least here, you're competing against a fixed best in hindsight. There are extensions where you compete against changing best in hindsight. Do you have any comments on that?
Yeah, so I have few comments, but not many. So some of this work can be extended to the moving window. But the computational aspects do not go through as well. But I totally agree with you that this assumption of the fact that things are changing, but I'm holding myself accountable to a fixed benchmark is not optimal. I have some other works about kind of relaxing this adversarial assumption on changes and then changing the benchmark slightly. And we can talk about that more offline if you want to know kind of other benchmarks that could be used here. But that's a very valid and very important question.
Maybe just another question?
Sure.
What is the computational complexity for algorithms a function of D?
Here, hold it.
As a function of D?
D and T, yeah.
D and T. It's a poly D and T, and it's something like square root of T times D, but there is some additional, I think maybe the square root of T could be like T to the 2/3. It's still like, it can go a little bit higher up, but it's a polynomial in both D and T. That's a cool thing. Okay, so let me move on to the next part of the talk. And so far we talked about how can I sort of survive the fact that people are changing their behavior. And in the next part of the talk, I want to do more than surviving. And I want to actually encourage good changes in the environment rather than just tolerate them. And this is a joint work with Brendan Lucier and Nicola Morlica from Microsoft Research and Jack Wong, who is now a PhD student at Cornell, and when he worked on this was an undergrad at Harvard. So a lot of the classification problems that we think about, their main point is to identify some kind of an attribute from visible features that they can see. When applied to people, this attribute that they're trying to find is typically some notion of qualification or excellence. They're trying to identify, for example, in candidates who are applying to colleges, which one of them are more likely to succeed, which one of them has the qualification needed. This is also true beyond college admission. For example, when recruiters are searching for people to interview, they're looking for people that they think are going to succeed. and many more of these identification of qualification and excellence tasks. At the same time, when we're thinking about people, there is the secondary role of classification, which is that people who want to be classified in a certain way, people who want to get admitted to universities and who want to get a job, are going to actually try to meet this measure of excellence that was identified by the classifier. So now the classifier is playing two roles, both to identify qualification, but also it is implicitly encouraging people to seek that kind of a qualification. For example, a student might want to study to get into a college. Or a person looking for a job might want to take some degree courses so that they can increase their chance. And when it comes to more traditional machine learning, this first part of the role of classification, which is to identify qualification, is something that's definitely been embraced by machine learning researchers as the primary goal of classification in some sense. And the second part, which is the fact that there could be these dynamics that are changing the features, has been thought about as this, sometimes as this thing that needs to be dealt with. And one of the reasons for this is this well-known and well-accepted law called the Goodhart's law, which says that anytime a measure becomes a target, it ceases to be a good measure. What that is saying in some more words is that a person's true features are some immutable object that just cannot be changed. And anytime, and my goal is to actually find that immutable object and make decisions based on it. So anytime somebody is actually changing them, those changes are all fake, and they're just making it harder for me to understand what was encoded in those features. And that's a failure for my algorithm. In other words, when you're thinking about studying, if you cheat on a test, that's like the type of fake change that didn't really actually change your qualification, but would have changed your appearance. And there is very good reason to believe this Goodhart's law. This is the reason we want to have robust learning algorithms that can work in presence of adversaries and potential malicious adversaries with malicious intent, and many other reasons for this. This has also led to a very important and influential line of work actually started here from people from Berkeley called the strategy-proof learning. And where the question is, how can we think about, again, creating learning algorithms that have that are robust to strategic manipulations that people may be taking. But what Goodhart's law is not capturing is the fact that in many applications, these changes that can happen are actual real changes that change the qualification of a person. So to have in mind, you can think about how studying can actually make a person much more qualified for the type of job or the college admission that you're thinking about. So these are scenarios where the actual object of, the actual feature representation just shows the current level of qualifications of a person. And a person can exert effort to improve this current state of the world. And this is important because through this kind of an incentivization, we can definitely increase the standards or the level of qualification through a society. So we should definitely embrace these real changes. So the question we are going to talk about is how can we find classifiers that incentivize agents to improve their qualification? And this hasn't been thought so much about from the machine learning perspective, but actually the economic perspective goes back, is pretty rich there. So there are Stackelberg games where we think about setting policies that encourage good behavior or discourage some bad behavior. But also there is this whole line of work on contract theory that says what kind of contracts that I write people would want to actually follow, even if I don't see exactly what they're doing. And in fact, this line of work has led to a very recent work that I find very interesting by Kleinberg-Ragavan about incentive-aware classification, using this kind of a principal agent model when you're working with one agent who you're trying to incentivize to do a good action. We'll take a slightly different view of this. We work with a model that actually works with distributions of agents that we are trying to incentivize. And we think about a person's underlying features being some vector x. And there's this quality metric that, let's, for this part of the talk, assume that it's known. It's a quality function that takes all the features of a person and will tell us whether or not they were a good candidate. However, I don't actually see this underlying features. I see some visible features that I need to use for my classification purposes. So maybe the visible features I'm going to see is some projection of this and this original features on some lower subdimensional space, lower subspace. And the mechanism that I'm going to announce is something that will classify a person based on the visible features. So you can think about the underlying features could be their homework, exam score, the number of hours they spend studying, all these things that you may not be able to see, where they volunteered. But their visible features would be their GPA and maybe their class rank, but I don't know how many hours they spend studying. So I need to make decisions based on these visible features, and I actually want to choose a classifier, a mechanism for classification that's coming from a fixed set of classifiers. So incentive-aware classification basically says that people can improve this observable features because they want to get a better outcome. And to do that, they're of course doing this kind of an underlying change. So we assume that there is a cost about going from x to x prime. And for the purpose of this talk, we assume it's L2 cost, but we have some more extensions. We assume that a person best responds to a mechanism, a classification mechanism that's announced. And what they're doing is that they basically take the action x prime that gives them the highest classification that they want, of course, minus the cost that they have to pay to change their current features to the features that would be used. And then the goal of classification is to maximize the expected quality of this improved features. This is the social planner's perspective. And more formally, it's shown as here as basically the expected quality of the responses of people. And there are many other actually goals that you can have in mind that I'm not going to go through, but they're also very interesting. So the challenge that we are going to think about is, first of all, is there a mapping between quality to the classification mechanism that I can just follow without looking at people's distribution? It turns out that that's no, but it depends on the types of mechanisms that we are thinking about. And then if I do need to look at the distribution of people, first, how much information do I need to know about this distribution, and how much computational power do I need to have?
So I'm a little confused because I can't tell, are you looking at it from the viewpoint of the student, or are you looking at it from the viewpoint of the admissions committee?
The admissions committee. So we are taking the role of the social planner, not just even the admission committee, but let's say somebody sitting in the Department of Education. What kind of admission can actually help increase the qualification rate of all students across? Yes.
Along the same lines, suppose we want to admit students that have a maximal product between intelligence and creativity. Do we really have any clue how we measure creativity or intelligence in such a way that it cannot be gamed and that it really leads to real improvement?
So the question you're asking is, do I even know this quality? This is a very difficult thing to talk about, and I agree with you. And in the third part of the talk, I talk about when this is a very hard to explain, but people have some intuition about it. So that's a very good question, whether or not quality is some function that we can write down. In some applications it might be, but yeah, I agree that sometimes in admission, like probability of success being written as intelligence is a very difficult thing to do. Okay, so going to the first question is, can I find an optimal mechanism by just looking at the quality without looking at the distribution? It kind of depends on the type of mechanisms that you're thinking about. So if we have a set of linear functions as a mechanism, so these are just linear rewards, then they incentivize everybody equally in the same direction of the linear function. So if you were working with these mechanisms, all you needed to do is to actually find the projection of the quality function on your subspace. And that would have been your optimal decision. But if you're working, for example, even with just linear thresholds, that's not the case anymore, because only people who are sufficiently close to the decision boundary are incentivized to move. And this is a very non-uniform way of incentivizing people. And in some sense, I need to know actually the distribution of people who are falling in this margin. So because of that, I need to know more than just the quality. I need to know the distribution of agents. How much information do I need to know about the distribution of agents? Well, we only need to know the visible features because that's what we are going to be working with, so just the projections of them. But also, you can pretty much just deal with samples that are coming from this distribution. And what's interesting is that if your original decision mechanism, like the linear thresholds, had low intrinsic complexity, which meant low sample complexity, you can show that the function that takes the quality of the improved feature also has a low intrinsic, low pseudo-dimension complexity, which means that it can be learned from very few samples. And at a very high level, that's because this, if you're thinking about this as the classification mechanism, your utility is basically 0 outside of the margin and a linear utility within the margin. So if this is simple looking at a very high level, this is simple looking at a very high level. And at a very high level, simple looking functions can be learned from data from few data points. And you can show that you can learn this with number of samples that's very small in the number of visible features and the accuracy level that you're looking for. And how about computational power? This is actually much more challenging in the sense that I kind of need to know and maximize the number of people who are falling within the margin, because those are the only people who would be moving. And this is known to be a hard problem in machine learning. But at the same time, this is also a pretty routine type of task that people do. Finding regions of dense regions of data is something that people do a lot in applications of learning. So if you assume that you could do this type of an optimization, you could maximize density in some margin, then what that tells you is that you could actually use this kind of an oracle to maximize density, and it would kind of give you an approximation algorithm for finding the best, approximately best classification. Yes.
So there's something here I'm not getting. Every year, the University of California has over 100,000 applicants. So there's a huge amount known. This goes year after year. So they've collected a huge amount of data. What is there not to be known?
About the computation?
No, I don't know. You're adding additional knowledge. What is it? What can you possibly add to the University of California? They already have.
So in the third part of this talk, I'll add something to the Texas university system. Not California, but close enough in terms of the size, hopefully. There are observations that have gone amiss for a while. Some of them have been caught, some of them haven't been caught. And we recover some things using machine learning that domain experts had recovered after months and months of working and thinking about policy setting. So let me talk about the third part of this talk to answer that question, but kind of to wrap up this part, and I know that we're running late, so I'm gonna run through the last part of the talk. But this part of the talk, we just kind of wanted to think about how can I incentivize good dynamics, and depending on data, the optimal mechanism could really look different for different types of data sets that you can be seeing. And we show that it's okay because you can still learn and optimize the optimal mechanism using almost the same amount of computation and samples than you would have needed to even just, even if you forgot about the dynamics of it. So for the third part of this talk, I want to come back to this question of, human decision makers have been deciding, who should get into university and who shouldn't for a while. What can we add to what they've been doing? And this is a joint work with Christian Borges, Jennifer Chase, Adam Kalai, and Ellen Bittersek. And Ellen is a PhD student at CMU and was an amazing intern at Microsoft during this period of time. And on day-to-day basis, human decision makers are using data sets sometimes to make a lot of these decisions that sometimes we are thinking about replacing them. Day-to-day basis, you can think of a recruiter going on LinkedIn, looking for a computer programmer with 5 years of experience. So these are search criteria that they're using to find some group of candidates they think are qualified. This is really important because when it's hard to talk about that quality function as a function, human experts seem to kind of intuitively know what is a good quality by just looking at people rather than explicitly telling me what kind of a function would be the quality function that I'm thinking about. And this is especially important when we are dealing with unlabeled data sets that show the features representation of people, but don't tell us whether or not these are good or bad students, because we haven't actually tried these students. They haven't gone through our system yet, and we don't know enough about them. So we want to think about this kind of a search criteria that human experts are using. At the same time, while these human experts have the domain expertise and can use explainable search criteria, they have the human inefficiencies of potentially sometimes being biased against some kind of demographics of students, but also inefficient. On the other hand, algorithms as decision makers can be both efficient, and bias in algorithms can be detected, even though it might be hard to fix it if you don't know the quality function. So what you want to do is to, rather than working with one or the other, to actually merge their powers. And the way that we think about augmenting this human decision-making power is that we work with these people who are making these selection criteria, M. So this is like, looking for a computer programmer with more than 5 years of experience. And then we want to find a different search criteria, like web developer with more than 2 years of experience, that captures both more diverse set of candidates, but also returns candidates that are similar in quality to the original search criteria. And I'll talk about that a little bit more. But what that looks like is that we basically use the system to take the original search criteria and return a suggested search criteria M prime. And to increase the diversity or even measure it, we are using the data set to decide how we should be broadening the search criteria that human experts are using. Algorithmically thinking, we have a distribution of candidates with their features and protected attributes. And we want to have the selection criteria to accept or reject them. And we want to think about different search criteria, this M prime, that doesn't directly look at the protected attribute like race or gender, but and it's coming from this predetermined set of structured, principled, potentially explainable mechanisms for admitting or not admitting people. The high quality, I said that we want to have high quality candidates being selected in this search criteria. It's kind of hard to talk about high quality when the notion of quality is not there because we are working with unlabeled data. So instead, we think about just symmetric difference of accepted groups or just other ways to compare our current suggested criteria to the criteria that was inputted. And in this way, we are basically relying on the human knowledge and intuition of having good search criteria, but just trying to broaden the search criteria to capture more diverse sets of people. And the diversity could be about the distribution of the protected attribute in the accepted groups. I want to tell you a little bit about two experiments. One applies to the college admission policy in Texas, and we're working with University of Texas Austin applicant data. If you think about the typical way of admitting students, which is based on SAT score or ACT score, you see that an SAT score, for example, 55, doesn't actually have that much minority students in it. It's only about 11% minority. And let's say that we want to increase the diversity of this to 20% while minimizing the change between the number of new candidates that we are admitting. And if we enter this into our system, what comes back is that the suggestion criteria is to actually use the top 10% class rank rather than SAT or ACT score. And this is not some hypothetical thing. What we recovered is actually the Texas 10% rule. This was a law that was made into a law in like 1997 because the University of Texas system needed to increase its diversity of candidates, but it didn't know a good algorithmic way of doing this. So they actually talked with a lot of domain experts and decided that accepting based on class rank increases diversity. And years later, this law has been praised as both increasing diversity and actually the quality of students that are being selected and admitted to Texas university system. So I think this is really cool that we algorithmically recovered something that domain experts recovered after studying. You can think of also job application, but here we are thinking about the distance between two job applications being the set skills that are required for them. So the Department of Labor actually has this kind of a tree that tells you how close math teachers to CS teachers are. So now you can think about if I'm working and I'm looking for computer programmers, I see that only 20% of computer programmers in United States are women. But if I want to increase that, maybe I should also think about searching for web developers. Maybe I should be thinking about computer system analysts. Maybe I should be thinking about operation research analysts. This kind of a principal way of broadening the search increases the diversity. And this is kind of the Pareto front of like increasing diversity at the least cost the change to the type of skill set that you're looking for. The same thing can happen when you're thinking about jobs where the fraction of men is quite small, like social workers, going to community and social service occupation and more. Let me skip the last part of this. There are some questions that are very important about both learning and optimization in this setting. I guess let me talk about the important one here is that we do need to access, the way I talked about this problem, we are accessing this protected race or gender attribute of people paired with their features X. This is rarely available in practice. And the reason we can actually do this, and we can do it in a responsible way, is that our methods don't actually require this paired presence of feature representation and the protected attributes of a person. Rather than thinking about looking at a protected attribute of person, we use historical data, and historical data that is just about diversity of candidates within a special criteria rather than the gender attribute of each person. So we can definitely do this in a responsible way and learn good criteria without looking at very private information. There are also optimization questions as to how you can do this in a fast way, but let's take that offline. And just to wrap this up, what we did is that we enhanced human decision-making via machine learning by relying on the human judgment of collective quality while correcting the bias or broadening the group of people who are selected by humans by giving them suggestions as to what they should be trying. And with that, I wanted to thank you for staying here, and I'm happy to answer questions.
Okay, let's have some questions. And I'm particularly interested in getting questions from students. Why don't I lead off the questions?
Sure.
So universities are not flying blind because I'm sure they're allowed to look at the records of students who have graduated, maybe anonymized, but you can, when the high school student fills out an application, it takes hours.
Yeah.
They're revealing so much about themselves. There's a huge number of inputs.
Yeah.
The universities, as the output, they say, well, how did they do? How did they do over the 4 years at the university? And so they can get a huge amount of correlations between the inputs and the outputs. So the university is in a very good position to try to do these things.
So
what can be added by this?
So actually what can be added is what universities are pretty bad at, which is the populations of people who they have not admitted in the past and they don't have enough information about. Yes, you're right. We are particularly good at looking at people who went through our program and succeeded, and we know that they did really well. But looking at the populations of undergrads right now in computer science, we don't have enough diversity. We do not actually know how to measure the quality of people who are not coming from the sets of features and things we have seen in the past. So working with labeled data of students who've gone through our system has this huge bias in it that can just exacerbate what groups of people will admit, and which will exacerbate by further, for people not wanting to even apply to then the UC Berkeley system or the Texas system. So the benefit of working with unlabeled data is that I don't make assumptions that I know, how people did. And this allows me to still have that human, intuition about what are good students, but then at least broaden my search using unlabeled data that has less bias in it.
Okay, very good. Let's see, some more questions from students? Faculty?
With respect to the first part of your talk?
Yes.
So you have told the auction houses how to really push the system to maximize their profit. Now, I have a feeling in this particular audience, there are fewer people running auction houses than actually clients of these auctions.
Yeah.
What advice do you have for us clients so we get what we want at the best possible price?
So I only, I only actually talked about revenue maximization, but the work we do is actually much broader, and it applies to both welfare maximization and also for acting in an auction. So I'm not going to go into the details of this, but the same kind of idea holds, which is that if, as a bidder, you kind of look back at the historical data and see how you should have bid it, and now you kind of perturb the historical data, that should be the way you should be bidding. So I just want to say that I presented revenue maximization, but actually that line of work,
to come back and give us the other
that's a very broad, it applies to a bunch of different optimization, even goes beyond auctions, and it's about just combinatorial problems as well.
Thank you for the interesting talk. I'm curious about, I guess, your second part of incentivizing good dynamics with by moving your classifier around. So you mentioned that you assume there's a cost of how much each subject, each applicant or whatever can change their underlying features, and that you go and look for the people like the clusters of people that can move. But I'm wondering, so going back to college admissions as a running example.
That's a very good question.
Like the people who can, push themselves over the edge. So basically the resources available for getting, for improving your college admission chance are not equally distributed. They're not fairly distributed, and you'll be able to find a lot of people who are just able to drop two grand on an SAT prep course or something. And I guess my question is, how can you augment your method with a sense of fairness based on, like relative costs between people?
So this is a very good question, and one that has been answered in strategic classification, but I didn't talk about it in the incentive-aware classification. And there's actually work coming from Berkeley, from people in this room, that shows that in the kind of the fake version of changes, actually, both from here and I believe also from Harvard and Microsoft Research, so let me give the proper credit, that shows that kind of subsidizing sometimes has these weird effects that even if I subsidize the cost of movement, if these movements are quote unquote fake, they don't actually reveal enough information about the underlying features, I can get to a worse set of dynamics and worse equilibrium. What happens here is that since the changes are actually real, if you do subsidize cost for people who are disadvantaged and just make sure that the cost is equal over all populations, then you can still apply this method and you do get at a better equilibrium. So it's kind of an intervention. I'm telling you that you cannot apply this method directly, but what I'm telling you is that the typical thing that people talk about, which is to subsidize or to separate to advantage and disadvantage groups, both actually happen to work well in our setting, although this is not the main objective of our study, and I definitely think that there needs to be much more work on understanding the effect of this incentive-aware classification on whether or not it has disparate effect on people coming from different populations. So I think that's a very important direction for future work.
Okay. Oh, one more.
So the last part of the talk, the whole talk was very interesting, but the last part of the talk I was particularly interested in. And one of the things I'm wondering is, you gave a positive example of how you can increase diversity by making this change. But let's imagine for a second that some other actor, not anybody in this room, was evil and they wanted to do the reverse. They wanted to exclude some group of people, but they didn't want to be detected doing it. So what they do is they go and they read this research and they figure out, they find a change that will exclude, that they can now predict will exclude a certain group of people or do something else that they shouldn't be doing. It doesn't even have to be excluding someone, it could be some other context. But they found a change now that will cause something that they shouldn't be doing to occur. And but it doesn't look obvious. Like it's not something as simple as just increasing one thing. It's some complicated merge of many features. And now we want to detect whether or not they have contrived to do something that they shouldn't do. They can stand there looking innocent, say, I didn't do anything evil. I just, made some changes, rebalanced these things. It seemed like a good idea because some made-up excuse. How can we come up with a measure of how likely it is that
the thing that happened as a result of their change is accidental, not deliberate, versus they found the one little narrow way they could do the one thing that they're not supposed to do.
So let me give you a couple of answers. First is, thank you for bringing this up, especially because it allows me to tell you that the third part of the talk is called green lining, and what you're saying is called red lining. And it's something that you're absolutely right. It happens. People get caught doing it. It happens. So one way I think about this is that the bad thing is already happening. So let's try to make the good thing happening as well. How to detect it. So partly for us, how to not kind of get into the bad part of it is to assume that the decision rule that you're making has to be something simple. So I couldn't say that, oh, I'm admitting people whose SAT is 95. Sorry, I don't even know the range of SAT. Is it 1600? 1800?
2400.
Oh, wow, I would have been really bad at it. Okay, so let's say their class rank is 95 and above, but also if it's 61 to 61 and a half. So I'm not doing this weird thing, so it has to be not just monotone, but it has to come from a set, I said explainable, set that is predetermined. So it's part of that just so that you cannot do this like kind of an arbitrary, red lining of adding parts that you want and subtracting parts that you don't want. Beyond this, I don't work on this line of work, but I think what you're saying is also very closely related to gerrymandering, where you actually can draw lines however you want to. And there are some mathematical models of how to do this, although that's definitely not my expertise. But I think if you're allowing any kind of, if there is no regularization, if you're allowing any weird way of drawing your drawing your line, I would say you need to look at the experts in that field.
Okay, with that, let's thank Nika again.
Yeah, thank you.
So your answer to my question